Good afternoon, everyone. Good morning, good evening, depending on where you're at in the world. My name's Jim Sluka. I recently retired from Indiana University. I was a computational biologist in James Glazer's group. I am going to give kind of a wide-ranging talk today, mostly on best practices for parameterization and doing CompuCell model development in general, and then also some slides about initial slide layouts. Let's see where I am. There am I. So talk about hints and tricks for simulating with CompuCell, some best practices and parameter file hints, and initial slide layout. There's a whole bunch of other slides in this deck. This deck is 119 slides long. I'm not only going to do less than half of it, but you're interested in writing to files. There's some slides to take a look at. Writing to a log file if you're trying to have multiple runs right to the same output file. Some slides on how to set up parameter scan and how to do replicate runs using parameter scan and how to do parameter sensitivities, perhaps with parameter scans. So hints and tricks. First hint is when you set the number of MCS, always add 1 to it. Oops. So do 1,001, 10,001, 100,001. That's because you often want steppables are done in integer multiples of 10. And if you tell it to do 1,000 steps and you have something triggered every 10, there's a possibility on your last simulation step that some of those things won't trigger. So do one extra Monte Carlo step to make sure that your last steppable runs and you've got all your output that you're expecting. In neighbor order in the basic pots, you should use a neighbor order of either 2 or 3. That will reduce what's called pinning to the lattice. The cells will be less likely to try to be absolutely perfect squares or cubes, and more likely to get a more physiological roundish shape, at least as round as you can get on a square lattice. CompuCell can use multiple CPUs in the pot section or the metadata section of the XML. You can tell it to use an increased number of processors. This does not always accelerate how fast the simulation runs. On a Windows machine, it will definitely use more CPU, but it will not necessarily run faster. So if you do use multiple processors, it's a good idea to check if it's actually helping. At the end of a CompuCell run, if you scroll down to the bottom of the command window and then scroll up a bit above the movie making code report, there's a performance report. And you can look at the total runtime and compare that to see if that number is changing as you change the number of processors. Different operating systems track CPU usage differently. To absolutely positively understand what the timing of your code is, the best thing to do is to look at the timestamps on any screenshots you're saving. That will accurately reflect how long it took to run the simulation. So you look at the timestamp on the first screenshot and the last screenshot, take the difference. That's the elapsed time, and that's actually the best metric of how fast your code is running or how slow it's running. And that's the number you'll want to look at and see if it changes if you change the number of processors. Steppables can be very slow, especially if you're doing things like visit all pixels or visit all cells. Visit all pixels in particular is very slow. One of the things in the timing report is the time per steppable. So this particular simulation had one steppable called CC3D parameters example steppable, and it used a total of 18% of the CPU time. You want to take a look at this number and make sure it's not too big. It's easy if you're doing a lot of pixel-based manipulation for your steppables to be using up the majority of your CPU time. You really can't affect too much these other runtimes, how much time the C++ code takes to run, etc. But you really want these bottom 3 to be using up the majority of your CPU. If you're getting really big time spent in your steppable, you might consider rewriting your steppable so it's not doing stuff so frequently to get it to run a little bit quicker. In general, steppables rarely need to run any more frequently than every 10 Monte Carlo steps. There are cases where you might want to run faster. But in general, every 10 steps is adequate. And sometimes every 100 steps is perfectly adequate as well. And that will keep you out of your steppable code and reduce the amount of time the steppable code is using. You do have to take into account, though, if you're only doing something every 10 Monte Carlo steps, whatever it is you're doing has to be 10 times bigger. So if you were drawing your cells at 0.1 pixel per every MCS, but you're only updating the target volume every 10 MCS, then you need to have it increase the target volume by 1 instead of 0.1, since it's only happening 1/10 as often. There's a couple ways to control how fast or how often a steppable runs. In your project Pi file, there'll be from whatever your steppable folder is, import some steppable name, and you can change the frequency that steppable runs automatically. Alternatively, in the steppable file itself, when you define the class, the steppable class, you can change its frequency there. I think probably the most common way that people do it, though, which has a little more flexibility, is to set both of these to 1, and then in your Python code, do modulo arithmetic to decide how often you're going to do some piece of code. So for example, MCS %10 is modulo arithmetic. If that's 0, then the Monte Carlo step number is an integer multiple of 10. So you're going to run some code every 10 steps, or some code every 100 steps. Or you're going to run some code every 10 steps, but you're not going to run it on the first Monte Carlo step, your initial setup. So this gives you, doing it in the steppable itself gives you a little more flexibility about how often you run things. It's important that you define your basic units. The most recent versions of CompuCell actually has a function now to do this, to define how much time one Monte Carlo step represents, or the width of 1 pixel. Even with that, it's a good idea somewhere in your code to document that I'm treating my model as 1 Monte Carlo step is 1 minute, and 1 pixel width is 1 micron, 1 micrometer. So it's a good thing that it's good to somewhere annotate that and write it down in your code. CompuCell does have a basic speed limit. You can't make cells move any faster than the speed limit. If you do, the cells will fall apart and start to fragment. And the speed limit's about 0.2 voxels per Monte Carlo step. So that's how fast you can get it to move. That's also roughly how fast you can get it to grow. If you grow much faster than that, you'll also run the risk of having fragmentation. So as I said, a reasonable starting point is 1 Monte Carlo step is 1 minute. But it depends on your model and how much time you're trying to simulate. It might be a day, it might be a second. The fastest I've ever seen is we did a simulation in the liver where 1 Monte Carlo step was 1/300th of a second, mostly because we had fluid moving in the model. In order not to exceed the speed limit in CompuCell, we had to have very small Monte Carlo steps. On the other hand, other models, a Monte Carlo step could be a day. Things might be happening so slowly that it'd be okay to take steps of a day. The question often arises, well, what should I set my Monte Carlo time equivalent to be? You need to look at your model and see if there's something in it that gives you a basic time frame. One common one is if you have cell proliferation, you can ask the question, well, what's the cell cycle time? How long does it take a cell to divide? Often that number is about 12 hours. Many cell types can divide in about 12 hours. So if you know how fast your cells can divide, you can then use that to estimate what your Monte Carlo step size should be. For instance, you might say, well, I want 1,000 Monte Carlo steps over the 12-hour cell cycle. And that means that my Monte Carlo step must be 43 seconds. So try to find something in your model that lets you calibrate time, at least as an approximation. It doesn't necessarily have to be highly precise, but you do have to know whether or not you're talking about a Monte Carlo step being 1 second or 1 minute or 1 hour. So an easy way to do it is just top your code in your Python steppables, just make a multi-line comment, and you can put anything in the multi-line comment you want. except for single quote marks or multiple quote marks. So you just go ahead and say, I'm going to assume 1 pixel is 1 micrometer, 1 microstep is 1 minute. Now, this is not being used anywhere, but you have at least written it down, what your initial thought was. You can also make that model definition into a named parameter. So now instead of just a multi-line comment, it's a variable that's a multi-line string. This is handy for doing things like printing out to a log file or something like that, so that you know what these parameters were. So best practice is trying to keep things organized and tracked. As your project develops, things tend to get fragmented, and you will try to do things and they don't work, and you'll try something else, and your code will drift over time. And it's a good idea to make an effort to track your code development over time and to keep track of your older versions. There's a lot of ways of doing that. If you're a hardcore programmer, you probably know about GitHub or SourceForge or some of the other code sharing repositories. These are specifically made for sharing code, so they have various tracking tools. They have checking tools if you want to write a checking tool. So they're out there. The tools are out there. If you know how to use it, they're great. They have robust versioning, automatically keep track of all your old versions. Just like I say, reliable retention of previous versions. And they're great for sharing with somebody else. A GitHub repository can be shared with anybody you want. It can be public, it can be private. Disadvantages are if you've never used GitHub or SourceForge, it's got kind of a steep learning curve. It takes you a little while to get used to it. It also requires internet access if you're using those files live, straight out of the repository. So hardcore programmers might do GitHub and SourceForge. Less hardcore programmers approach might be to use Google Drive or Dropbox. So it keeps you a reasonable sets of backups. So Google Drive will back up every old version or keep all your old versions. And in addition, Google Drive and Dropbox, etc., can all be shared with others. So you can share your code repository fairly easily. It can be very challenging to use Google Drive or Dropbox as the master, that you're actually running Twedit, loading files out of Google Drive. It can be done, but it's kind of tricky to get all those links to work. It requires internet access if you're using files live. And cost and quotas become an issue. So Google Drive, last time I looked, the free level is 10 gigabytes, which is a lot if all you had is code, but it's not a lot if you start generating screenshots and movies and things like that. So some of the free sharing can run into quota limits. Another way of doing it is just do it all locally. This is probably the easiest way, not necessarily the best way, but probably the easiest way, is to just keep old versions, periodically back up your code somewhere into a new folder or a zip file or something like that. So the advantage is it's easy. The disadvantage is there's a little protection from file loss. You lose your hard drive where all your backups are, you lose everything. It's little ability to trace the project evolution. It's a little trickier to do it that way. It's easy to develop broken code if you don't have old versions around. And it's not easy to share your local code with someone else. So one way to kind of do a little bit better job of that is to create local zip files. So you got your working directory on your hard drive. You just periodically take that folder and create a zip file and save it somewhere. So this is easy to do. CompuCell even has a zip functionality inside Twedit. So there's a menu option to zip the project up and create a zip file. You can give it a date, timestamp, and the file name, and keep track of when that particular zip file was made, what point in time it was. You can also go into the output directory of your project and zip that folder, and that folder will not only have all of your code, but all of the output that you had generated, like screenshots or anything else that you've been saving. So that output workspace directory zip file will have both the code and the results of running the code to the extent that you were saving results. The disadvantage of doing it this way, of course, you have to remember to do it. So you might want to develop just a workflow of after every main modeling session, you're going to make a new zip of the project and save it someplace safe. So as I said, you can go into your workspace folder, and every time you do a run, you get some output directory with a timestamp and a hash to keep the timestamps from clashing. Inside that folder is your top level CompuCell folder. Inside its simulation folder or your steppables and everything else that you might have been generating. If you're saving screenshots, those are also all in a folder. So you can just take this entire folder and make a zip of it and save your code, take a snapshot of your code and your output at some particular point in time. Now a little bit change, and now talking more about the biology. You should keep a working document that describes the biology that you're trying to model. That description should start off with what's the overall domain? Are you working on a cancer model? Are you working on a vasculogenesis model? What exactly is this model targeting in biological terms? And then in the same file, keep a list of all your biological entities. What are the cell types, diffusing molecules, extracellular, so physical objects and fields. And then a list of the processes for each one of those objects. Does a cell grow? Does it die? Does it secrete a small molecule into a field? What are all the processes in your model? And then finally, a simple image, nice cartoon of the model is very, very helpful. It could be, you could pull it up from, some image from the NIH about this process. You pull it from a paper. This cartoon of the model shown here was a collaborator I had. Toru Matsuura was interested in egg implantation in the uterine wall, and this is the cartoon he drew and gave to me to start with. And this is a wonderful starting place because it shows the spatiality, it shows the different cell types, it shows a progression over time, and it's a great way for the modeler to not only start building the model, but put a stake in the sand that says, this is where we started. This will be the concepts that we had in the model initially. Now, this cartoon can evolve over time and probably should evolve over time. But the cartoon is a lot easier to show somebody than a bunch of code. So one way to do it is just keep a Word document, or whatever your favorite text processing tool happens to be. If you keep it in the top level folder of the project, that Word document will get saved to your workspace every time you do a run. And if you're zipping the workspace, then that work document is saved into the zip. So you have a running track of this ever-evolving project description file. You can keep it as plain text, but the nice thing about doing Word or something like that is you can put in pictures and results and all kinds of other things into it that you really can't do in a plain text file. So best practices for parameters, keep a track of values and parameters notes. So tracking can be a challenge, especially if you start fiddling with parameters in order to get a particular output. You start to lose track of what you have tried and where you have been. In addition, the worst case biological parameters are just scattered throughout your code. And you've got two places in your code where you say your cell target volume is 10. Because when you initialize the cell, you tell it to be 10, the target volume to 10, and then later on you divide the cell and you're going to tell it to be a target volume of 10 again, but now that magical value of 10 is in two different places. And if you go in to change one of those and forget the other one even exists, then your code has a serious problem. So you don't want to have these things scattered about in the code and poorly documented. So what you want to do is you want to track and organize your parameters and clearly label the conversion between biological units and modeling parameters when that is applicable. So clearly state that 1 pixel is 1 micron. Clearly state that a target cell area is 100 square microns, which works out to be whatever the conversion happens to be for your pixel size. Keep that and organize that information somewhere in a logical way. In addition, when you're doing that, you should keep track of what are the units. The target cell target area is in microns squared. The cell division half-life is in reciprocal hour, or is in hours. The rate constant is in reciprocal hours. And in addition, you can add references. If you had to go look up how big your target volume is for a particular cell type, this working document is a great place to log that citation. So here's one approach, is to put all your parameters in one place. You put them in the top of your steppable files if you want to. So here I have seconds to Monte Carlo steps, and then a text description of what that means, a translation of the variable name. Days to Monte Carlo steps, voxels to microns. These parameters can be used anywhere in this Python file, the steppables file. Though if you want to change the parameters anywhere, you have to use a global keyword in the steppable. So here we make some definitions, and then we use those definitions to find the width of the model. So it's the cell biological width times the conversion of voxels to microns. So that's one approach, keeping all your parameters at the top of your steppable file, for example. Another approach, and one that probably works a little bit better, is to create a separate parameters file in Python and include it in your project. It's just another Python file. Your other modules can import the parameters file. In that parameters file, you can keep track of your units and your references. Ontological links. When I say long epithelial cell, this is what I mean. It's the object that this URL points at. So you can keep all that stuff in one file that's got the same goal throughout. In CompuCell, you can do that, or excuse me, in Twedit, if you right-click over here in your file list, you can add a resource. And you can give it a name. We'll call it parameters. It's a Python file. It'll be located in the simulation directory where your steppables file is located. So enter those two and hit finish. And now you have a new parameters file in your CompuCell simulation. So save and track with your simulation. Right now, the parameters file is empty. I've got it selected. So that's where you can start putting in your parameters. Make modified date, keep track of when you actually did this. You can divide the parameters into what are your biological parameters, so cell widths and the model width and things like that. Model parameters are conversions from biological units to computational units. And then you can do math. You can calculate new parameters based on your other parameters and use these new parameters to control your simulation. So this particular example we're trying to do is, instead of just saying our model is going to be 100 pixels wide, what we're going to say is our model is 10 cells wide. And a cell is 10 microns across. All right, using that data, I can calculate the model width in pixels. Everything is actually being described in biological terms. And then your parameters Python, you can convert that into the CompuCell values needed, the width of the model and things like that. Now let's me change the model. If I change this 10 to 20, the model gets bigger. The CompuCell window will get bigger. So here's the rest of that particular file. We got the basic biological parameters, defining the model in terms of biological concepts, like the width of the model is 20 cells wide. We got the pixels per micron and the time limit for the simulation. We can calculate the model width in pixels. We calculate cell width in pixels based on cell target diameter and your conversion of microns to pixels. You can calculate cell target volume, etc. And now if I change any one of the upper parameters, these later parameters change. In this particular case, I'm also changing adhesion value. So the J value for between the two cell types, M and M, and between M and C and M and N. And they're being calculated based on the size of they're being rescaled based on the size of the target cells. So to use your parameters.py in any other Python file, you just import parameters as some name. I use P, a convenient name. Notice there's no extension. It's not parameters.py. It's just parameters. Put in parameters.py, it won't work. For some reason, in Python's import doesn't allow you to give it an extension. In any case, so now this is imported, that parameters file, it's called it P, and I can reference anything in the parameters file as P dot, and then whatever the name is in the parameters file. So now I can set my cell target volume to be the value that's in the parameters file. Instead of hard coding in my targets, they're all being calculated and imported from the parameters file. If you're in, this is the Python version of the XML file. So you can do the same thing there if you're using a Python only simulation. So we can import my parameters and I can define the dimensions of my CompuCell model based on this value that was calculated in the parameters file. So if I make a change in the parameters file, the next time I run the simulation, this will get recalculated and it'll make the new a proper sized window for the simulation. So in this particular case, as I said, we're calculating the model width based on biological descriptions of how wide the model should be in cells and how wide a cell is, and the microns to pixel conversion value. And just showing it that these earlier parameters are being used later to calculate the model width. And this I already showed that you can use model width extracted out of the parameters file to change the model width. So Python only simulation, I think if you use CompuCell long enough, you start to run into limitations of what you can do in XML. In particular, it's difficult to programmatically change variables in the XML from Python. There are ways of doing it, but there are some of the things that are very difficult to change, like the model dimensions. It's a very tricky thing to change the model dimensions once the XML has already been executed. So when you're building a new simulation, you might want to consider using the Python only option, which puts the XML information into a Python file. That makes it much more easy to programmatically change things like model width and neighbor order and things like that. So if you do that, so this is a version of a Python only version, and this is the Python equivalent of the XML code. And if you're familiar with the XML code, it's pretty easy to find the things you want in this file. It's got the same kind of layout, the metadata block, the POTS elements block, the cell types block, the adhesions block. But now, since this is Python, you can use parameter names and calculations within this Python to set up your simulation. So I can show a quick example. In this particular one, this is the demo file. It'll be in the zip file. And this is showing an example of how these bits and pieces can work together. So this is a Python only simulation, and here's the Python equivalent of the XML. And for example, here's commented out the plugin for adhesion energies, all pairwise possibilities. And it's been replaced by using values that are being calculated in the parameters file. Here's the parameters file. So this Python imports parameters as P. My Steppable file also imports it as P. So this file can also access variables that are in the parameters file. See if it'll start up. This is just a cell sorting simulation. This graph is plotting the heterologous contact area between the cells. As the cells sort, the heterologous contact area should decrease over time. And it's a cell sort, it'll take a while to run. But the reason for showing this is I see right now the model is 100 pixels wide, and I think it's 5 cells wide. But I can go into my parameters file and tell it instead of 1 micron per pixel, pixels per micron. Let's see, what do I want to make it 2? No, make it a half. So now a pixel's only 0.5 pixels per micron, which means a pixel is 2 microns. And then save. Remember, it's 100 pixels wide right now. If I run again, now the model's only 50 pixels wide. So you take a look, and actually sorted. See, my heterologous contact area dropped and pretty quickly. It sorted really quickly with that pixel size. I'll write it again. Same settings. It sorted pretty quick as well. So this particular parameters, it's trying to estimate how the adhesion values change as a function of basically the pixel resolution, but also lets me change things in terms of how many cells there are in the simulation. So I'll make our model 20 cells across instead of only 10 cells across. Now my cells are the same size as they were before, but I've got twice as many cells, or actually 4 times as many cells, because it's 20 cells across and 20 cells time. So that lets us keep all of our parameters in one place. It lets us add things like what is the definition of these things, or cell width in microns, the unit is in microns. It lets you add a citation for PMID for a paper that sells, my particular cells are 10 microns wide. It lets you add ontological links and anything else you want in a kind of a free-form way, but at least you have explicitly defined what all these things are. And actually, this should be a 1. For my earlier comment, I always run 1 extra step. Right? So you might, this is an easy way this is put the effort in at the beginning of your coding cycle. Put the effort in to build a reasonable structure for your parameters. And it will come back and help you as your project gets more and more complicated. Let me change my share. It's this one. Okay. Hopefully I'm back to slideshow.
Looks good.
So there's a good way of tracking your stuff, and it will really help 6 months from now when you decide you're going to write a paper. If you have all that stuff that you had learned along the way, you pulled this parameter out of this particular paper, and here's the citation. And you made the explicit decision that your cells were going to be such and such a size. Your microns to pixels conversion was be a particular thing. And there are a lot of other things that you can do. This is just for reference. This is how I was scaling the J values, since that's one of the most difficult things to scale if you're going to change your pixels per micron definition. And it's basically just a linear scaling compared to some reference state. I started off with the cells are 10 pixels across. How does that change if I say a cell is only 5 pixels across? But that's in the parameters file if you'd like to look at it in a little more detail. So one thing you do with this particular example is you can study, well, how does the system change its behavior as I change the pixels per micron resolution of the file, of the simulation rather. If I make the pixels represent really big, 2 or 3 microns across, I don't get very many cells. I don't get very many pixels. The simulation runs very fast. If I make the pixels per micron smaller, I get more pixels per cell. The entire simulation gets bigger and everything runs slower. Often people will ask you the question, okay, you ran your model at 1 micron per pixel. Do the simulation results change if you change that resolution? And you say, well, I don't know. I never actually looked at that. This approach would let you do that. You would take some metric of the simulation and you just scan your microns per pixel parameter and just do multiple runs and see at what point does changing the microns per pixel stop having any effect at all on the simulation, other than the simulation getting slower and slower and slower. And you see across these 3, 0.2 pixels per microns, 0.5 and 1, they're getting to this about the same place, though the coarser simulation is taking longer to get there. And the finer simulation got there quicker. At least that's what it appears. But the actual sort results is very similar, especially if you don't especially if you use a little bit more pixels per cell than 1 micron per pixel. Then another nice thing about scaling your simulation this way is that when you're doing code development, you might want to get your simulation running fast, just so that you can get simulations done quickly to check your code. And this simulation will run considerably faster than this simulation will. In fact, this is probably 25 times faster than this simulation. So you can work out all your coding, figure out what you're going to track, do your debugging and everything else with fast simulations. And then by changing a single parameter in the parameter file, increase the resolution and run it at a slower simulation with a finer resolution without having to go through all your code and figure out, well, if I change pixels per micron, what are all the variables in my model that change in response to that one change? Let's see, take a quick look at some of the questions to see. Do I run into any problems if I do not define some of the parameters in the parameters.py file? You don't necessarily run into any problems. You just don't have a way of keeping track of what the parameters are, because now your parameter is going to be defined someplace else. You can't add into the parameters.py file programmatically during a run. Actually, I probably shouldn't say you probably can do it. You probably don't want to do it. But as a practical matter, you start off with your parameters.py file and you put in what you think you need, your pixels per micron and maximum MCS and things like that. And as you're working on your steppable, you come to the point where you say, oh, wait, this is a new parameter that I need. And I can calculate it from some of the other parameters, or I'm going to assign it by fiat to some value. Well, that should be moved into the parameters.py file and you should annotate how you came up with that value. And then in your steppables, pull that value back in from the parameters. So you can go around as you expand your steppable, you're adding more parameters in the parameters file, and you're using those definitions in your steppable file. Parameters change this way or read only, that's true. Though you can use, in the first approach that doesn't use a parameters file but uses global variables can be changed. Use the global variable, a steppable could change that global assignment. By default, you can read a global, but you can't write to a global. If you need to programmatically change the parameters.py file, I suspect what you'd want to do is figure out beforehand what that change is going to be and put the math in the parameters file. You can have a function in the parameters file. So you could call a function. For instance, your parameters file might have a function that returns all pixel coordinates for a circular cell, given a center point. So you put that in your parameters.py file. Now your steppable can call that function and generate the set of pixels for a new cell, for a circular cell or whatever shape you write the code for, so that your steppables is not cluttered up with this, kind of basic code that figures out all the pixels that are within a particular distance of a central pixel. So as I said, there's some complex interactions between the parameters in the POTS file. Things interact with each other. J values interact with lambda volume and target volume and surface constraints. So rescaling can be very tricky. But if for no other reason, just to be able to run the model very quickly is helpful as the model gets more and more complex and your code gets more and more complex. And you've got a final steppable that at the end of the simulation outputs your results. Well, you don't want to have to wait 3 hours to get a model run so that you can find out that you're missing a quote mark in your final step that was writing to a file. So it's nice to be able to run your models fast and to help with code development. So logging the parameters. If you do it the parameter file approach, that parameter file will be saved to the workspace directory for the simulation. So that workspace directory has all of your code, your steppables, your XML, your parameters, and any results like screenshots or any files that you had written. So if you make a zip file of that directory or copy that directory someplace else safe, you will have your parameters along with your simulation. There are more complicated ways. I don't think I'll go into a lot of detail here. Someday it would be great if CompuCell actually had a class called parameter. And that class would include things like what is the parameter name, the variable name that you use in code. What's the English translation of that? So what's the translation of pixels per micron? This is the variable name. What is the English translation of that? What units does it have? What is a citation to a reference database? What is a citation to, say, a PubMed publication? But to have a class, a Python CompuCell parameter class that carries all this information in an orderly fashion. So this is just an example of more complicated ways of building dictionaries that lets you keep track of more information about your parameter values. And so on this particular approach, you can actually tell it to do a pretty print on this dictionary and generate this table. So there's a lot of ways to do it. It's important that you at least start with what's my pixel resolution, how long is the Monte Carlo step, and things like that, and then build it up as you go along. And every time you find a new parameter as you're writing in your steppable, you really should move that parameter into the parameters file. If it's something that's not calculated dynamically, but is a fixed value. You can do multiple parameter sets. This is one way of doing it. If this is my parameter.py file, I can define my variables based on some controlling variable. I change the variable experiment, I use this set of parameters. I change this to 2, I use this set of parameters. And of course, this would be much more complicated. If we go back, this dictionary back here could have been a list of dictionaries where the index that tells you which dictionary to use is this experiment variable. And that would put all of our data into one big data structure. You could have multiple experiments. We could then print it out in a nice table that for experiment 1, pixels per micron was such and such, etc. It's worth the effort to keep track of your parameters in a consistent way so that you don't have floating parameters, magic numbers in your code that it has to be this particular number. I don't exactly know why, and I'm going to forget where it is in my 500-line Python steppables file. So magic number, put it in the parameters and say it's a magic number. It has to be this number. I don't know why. That's fine. But here it is in the parameters file. It's not hidden somewhere in your code. So establish a consistent process for tracking your code. Keep zip files, do a GitHub, do something. Every time you get a good run, take that workspace folder and zip it up and save it someplace. Make the effort to track your parameters and references as you go. It'll help you downstream when you try to write a paper of it. And keep a running Word document or some other document that's with your program goals, what you've tried, what your versions are, etc. Okay, so now we're going to switch gears and talk about initial cell layouts. CompuCell has a lot of ways of laying out cells. One way is Twedit has built-in initializers. You don't actually have to use Twedit to get the initializers. You can look up the code and put the code into your XML or into your Python. But Twedit is handy for building it initially. So there's a BlobInitializer. We'll go through these real quick. UniformInitializer, Tube, Polygon, and some other ways of doing it as well. So uniform and blob, usually it's in your XML, or your Python version of the XML. It lets you define a region, which is a square region, box min, box max, and then a list of cells that you're going to fill that region with. And the proportion of these cells is the proportion it will try to get in the region. So I got a mixture of A cells and B cells. So this A code creates this box down here. It's got a gap between the cells. I said my cells are 5 pixels wide and there's a 2-pixel gap. And so it randomly populated my A and B cells and C cells, actually the 3 cell types in here. And it made that box. You can overlay another region. So here's the B definition. And it overwrites the previous definition. Here's a square rectangular region of cells of type B. Actually, it's type C up here. The C region was a big square box. It was completely filled in. And then D was a region of medium, which basically erased the inside of the box. So you can build up more and more complex structure by doing things sequentially. These will be executed in the order they're written. So the final value for a pixel is whatever the last thing was done to the pixel. So this is UniformInitializer, which does rectangular regions. BlobInitializer does circular regions. You can do the same thing. Make a big field of some cell type and then overwrite it with another set of cells. And you could overwrite it with medium and make a hole in it if you wanted to. So there's a lot of ways to set things up with uniform and BlobInitializers. You can have multiple regions, later regions overwrite earlier regions. One thing you have to be careful when you're overwriting things is it's possible to get very small cells. You see it, for instance, this blue cell here is only half as big as it should be because half of it's been overwritten by the red section. You probably need code to deal with that. One way of doing it is after you've done all your layouts in your Steppable, iterate over all of your cells and look at how big the cells are. And if a cell is much smaller than it's supposed to be because it's been overwritten by something else, you don't even have to figure out what it was overwritten with. You just say, this cell current volume is only half as big as it should be. Then you can just delete the cell. Or do something with the cell so that you have some logical way of treating the fact that fractional cells get created when you're overwriting in this way. PolygonInitializer lets you define a set of data points that it will walk around and then fill in that region. So we're going from 10, X coordinate of 10 and 90 down to 10, 10, over to 90, 10, up to 90, 90. And then it continues on. It goes to this point, this point, this point, this point, this point. And then that polygonal region gets filled in with cells. And that works in 3D too. So if you can come up with a 2D projection that you can defined by a series of points, you can make the 2D version of it, and then you can extrude into 3D, but you can't do a complex 3D shape where it's not an extrusion from 2D. There's also a cylinder initializer, great if you're trying to make a vascular pipe or something like that. Lets you define, here we're defining two regions. The first region is the green pipe. And then inside the green pipe, we make the red cells, the B cells, which hollows out the pipe in type B. You could also hollow out the pipe by filling this region with medium instead of another cell type. Finally, there's two more. PIF initializers. So CompuCell has you may have seen them already, a file called a PIF file, which is just an exhaustive listing of what every pixel in the simulation is at a particular point in time. In a Steppable, this is XML. You can import a PIF file. So if you've got some complicated layout, your XML file can import that layout in the XML or your Python version of the XML to get your starting configuration of your files. CC3D can write a PIF file. So again, if you're trying to generate some initial complex structure, it takes some computing to do, but ultimately that's just the starting. You're just trying to generate the starting point. You can do that as one run and save that starting configuration, and then have a separate CompuCell project that starts with that configuration and moves on from there. In addition, you can write your own code to generate a PIF file. The syntax is pretty simple. It's a cell number column, so cell 0, cell 1, cell 2. The cell type name, so this was a medium. This is a cell called foam, X and Y and Z coordinates. You can specify individual pixels, or if you use X1, X2, Y1, Y2, you make squares and rectangles in 2Ds or parallelograms in 3D. So you can either specify every single pixel or square regions within it. If you have cluster cells, there's just an extra starting column that tells what cluster it belongs to. So these first 5 lines are 5 different cells, but they're all part of the same cluster cell. This looks like so this particular cell has a center, a top, and a bottom, and 2 sides. So you can write this PIF file any way you want, from some other Python code, from Excel, from anything you can think of to generate this PIF file, import it into CompuCell and get your initial configuration. You can manually create cells in a simulation. So there's a one-liner available in Twedit and the helpers for the cell manipulation. It just inserts a line like this here, just says the cell field. So cell field is the array. It keeps track of the cell ID of every pixel in the simulation. And this is saying pixels 10 and 11 on X and pixels 10 and 11 on Y, since this is a range that doesn't actually get to the final value. It sets it to a cell of type name, cell type name. So type name is one of the cells that you defined in your cell types in your XML. So if you know what the type name is, go ahead and do it that way. There's a more complicated way, a way of doing it with more control. In this case, you create a new cell without putting it anywhere. Again, there's a helper in Twedit that will put this code in for you. You say, I want to create a new cell. So cell is new, and type name will be replaced by my cell type names. It's an epithelial cell, so it's self.epithelial. Some positions and size for it. We then assign that the cell field, the pixels in this particular range of the cell field, to this newly created cell. We created a new cell. We probably need to remember to assign a target volume, a lambda volume, and target surface, etc. What other things you have associated with the cell, you'll need to assign them to. You can change the cell field anytime you want, and you can change a pixel to be a pixel of another cell. So here we're showing an example. Change this XYZ, this pixel at XYZ, into the cell 2 ID. So now that pixel is a part of cell 2, regardless of where it's in the field. It might be far removed from the rest of cell 2, but it is part of cell 2 now. You can assign a pixel to medium. This is kind of obscure by assigning a pixel to the Python type none. Basically undefined, which is what how CompuCell treats a pixel of mediums. The cell ID is undefined. So if you ever need to write pixels of medium into your simulation, this is how you can do it. They said if you create a new cell, remember you may need to set target volume and lambda volume. Though whether or not you need to do that depends on how you had set things like volume initially. If in your XML you explicitly set target volume and lambda volume, etc., by cell type, when you create a new cell, the new cell will inherit those targets. If you're doing all of your targets definitions in your Python steppable, which means in your XML, you've got a line like this. You load the plugin, but you don't give it any parameters. You don't tell it what any of the target volumes are. If you're doing it this way, then when you create a new cell, you have to make sure you set the target volume and lambda volume, etc., for that new cell. So here's a little bit of sample code that in Python that generates this set of cells. So it's reasonably straightforward if you can come up with a way of coding where your cells are and how to pick pixels around the center. This particular one simply sweeps an angle through 360 degrees. It's got a target number of cells on the circle and a radius, and it generates a center, and then around that center it draws a circular region of cells. It creates a new cell and fills that cell with those pixels, or assigns those pixels to that cell. So arbitrarily complex. It's only limited by what you can figure out how to do in Python. A couple of warnings if you're manually manipulating cells. CC3D used to not check to see if a coordinate is inside the limits of the model or not. It wouldn't even throw an error, it just crashed. I believe that's been fixed. I think now if you tell it to assign a pixel outside the model, it'll throw an error and at least tell you that what you did wrong. So it's up to you to make sure that any pixel you define or any pixel you attempt to access, it's up to you to make sure that pixel is actually within the model. There are self-dim X, self-dim Y, and self-dim Z global parameters that tells you what the X width, the Y width, and the Z width of the model is. So if you're generating in Python as pixel coordinates, before you actually reference the cell field for those pixels, you should make sure that your pixel is greater than 0 and it's less than the maximum dimension on that axis. It's a little more complicated. It's possible to import an image. CompuCell is running in this Python script, so anything you can do in Python, you can do with a CompuCell model. This is not necessarily easy, but it can be done. This is an example of, this is a 220 pixel H&E stained histology section. I write a little bit of Python code and import this image in. CompuCell doesn't have real good rendering capability, so here instead what it's showing is this is the red channel from this image. This is the green channel. No, this is the blue. I'm reading my caption. This is blue channel. This is green channel. This is red channel from the RGB input image. And then this is all the channels summed together. CompuCell only has one color bar. So our only choice is blue to red. So there's no way to actually redisplay the image with the original color since we don't have that color capability. But these are accurate images of versions of this image, given that we're looking at the red, green, and blue channels. We're just limited by the one color bar that CompuCell has. So how you do that is, well, like same way you'd import an image into any Python code. One way is PIL. There's also CV2 and a couple of other image processing libraries. So you can come back and look at my slide deck later if you want to figure out how to do this yourself. Basically means you have to install the new library in CompuCell using pip or whatever your favorite installer is. Once you've installed the image library, you can import that library into your Python, your CompuCell Python. And now you can read an image in and you can go from there. PIL and some of the other libraries don't support GIF images. They support JPEGs and PNGs and a lot of other formats. This is actually the code for it. So at the top of my Python Steppable, from PIL import image, I make a new image which uses this image module I've imported and my file name. A little caveat that in the imaging world, the origin is upper left corner. CompuCell, the origin is the lower left corner. Well, easy enough. You can take the image and flip it top to bottom. That way, in the image now is the origin is the bottom left. Iterate over all the pixels in the image and do whatever you do. Ultimately, what I'm doing here is remapping the three color channels. I create a scalar field for that image, and then I poke into that field the gray value for it. And you can do anything you want with it. You've got an array that's the image. You've got your self field array. You can do whatever you'd like to map from one to the other. So it's pretty straightforward. Once you get the image library installed, import the image library, import the image, start manipulating the image. So conclusion on initial layouts. So there's the BlobInitializer and the UniformInitializer, which do circular and spherical regions and rectangular regions. TubeInitializer does tubes, as the name implies. PolygonInitializer. You can load a PIP file that you created externally or a PIP file that you have saved from a previous CompuCell run. And you can manually create your cells in Python. It's only limited by how clever you can be in figuring out what pixels are supposed to belong to a particular cell. And you can import an image and use that as a starting point. Another way of using the image import would be, instead of having this histology image, which histology images are complicated, they have very wide color ranges and there's a lot of detail, you could just make a drawing in Paint or something that has black and red cells, for example, laid out the way you want, and then import that image into CompuCell and parse that image and create your cell field based on that image. So that can be done as well. A lot of ways of creating initial conditions. There are some exercises that'll be in the demos for this class. Feel free to look at them. There's a lot of different ways of creating cells. And I think I am pretty much done. This slide deck is huge. There's also a set of slides if you ever need how to write to data files. You can write to any file anywhere in your file system. There's a helper in Twedit to write to the workspace that is your normal simulation output directory, which is very handy. But you can also write to the main project folder if you want. Slides on how to do parameter scans, how to do replicate runs using parameter scan, and how to do parameter sensitivity, which can also be done with a parameter scan. So I think I will stop there. Let's see. Yeah, that is my last slide. So I'm glad to take any questions. I would say that if you ever have a complicated initial configuration and you're not quite sure how to do it, post a question into the chat, the CompuCell chat. someone trying to find something here. The CompuCell Reddit. Chances are somebody else has already tried to do something similar to what you're trying to do. So put a comment into a question into the Reddit, and someone often can help you figure things out, figure out a good way of going about something.
Yeah, so like Jim said, this slide deck has a lot of information in it that both that we covered and did not cover today. So if you have any questions about how to do any of the things we talked about today, make sure to revisit the slides. And if you have questions about additional features as well, they may be in that slide deck. So that will be a good resource for people, especially moving into the hackathon.
I see there's a question in the chat about how do you handle multiple timescales or widely divergent timescales. That's a really good question. It's a problem that I've ran into fairly recently in the ovarian modeling. Follicles develop over 3 months. Takes a couple of months in primates for a follicle to move from one stage to another, and there's 7 stages. So when thinking about the follicle, it takes many days for it to do much. So you might think, well, I might color step you 1 hour. So I've got 24 steps per day and it takes 28 days. That all seems to work out just fine. Unfortunately, the follicles also secrete steroids. And so I say, well, I'm going to have a field of steroid secretion. That's one of the ways that follicles communicate with each other and with the systemic, the rest of the body. But diffusion occurs at the cellular scale on the time steps of a few milliseconds or less. So we don't want to try to run a PDE with a 1 millisecond time step, and in a CompuCell model where the CompuCell pixel time step is an hour, because we're going to spend all of our time running that fast diffusion, running that diffusion model. So in that particular case, our solution was to say that the diffusing fields and our time scale are always homogeneous. And the field can go up and down, but the field concentration is the same everywhere in the CompuCell simulation. And we don't attempt to calculate the PDEs. That was our approach there. There are other approaches, and I'm sure James and some of the other people on this talk have run into, or on this session, have run into this problem before. How do you do vastly different time scales effectively? How do you do that effectively without spending a whole bunch of time calculating something that's on a real small time scale where actually in the long term it all averaged out anyway? Any thoughts, James?
I think, yeah, I think this issue of multiple cross timescales is hard. Your example of the liver was a really hard one, where you had to have this microscopic time step. In a lot of biological processes like neuroscience, you have separation of timescale where action potentials are so fast you can treat them as instant compared to everything else. Unfortunately, in a lot of developmental processes, the timescales are mixed, and then you wind up having expensive computation. In principle, there are ways of doing adaptive time stepping, but CompuCell doesn't support that kind of highly dynamic time stepping algorithm. Something that we've thought about over the years would be to have something like a quadtree octree decomposition so that the granularity of the simulation spatially different in different locations. And in principle, you could have adaptive time stepping as well. But in practice, those are things that kind of orchestration is complicated to do. People who do fluid dynamics, complex coupled fluid dynamics codes, do actually write those kind of complicated orchestrators. And there are packages like Muscle3 that are designed to support that. Vivarium is designed to support that. And CompuCell runs as a component of the variant. There was a question about complex three-dimensional shapes.
Yep. And what I would say to that is that I will bet that CompuCell will generate that shape automatically. If you tell it that in 3D that the cells are cubical, and then relax the field, I bet it will recreate that shape or something close enough to that shape to be usable. If you take a square in 2D, if you take a square lattice of cells in a neighbor order of 2 or more, the cell field will relax and the cells will convert from being squares to being hexagons. And if you look at histology slides of tissues of homogeneous cells, cells are hexagonal in 2D sections. So CompuCell will generate in 2D the correct basic shape of the cell. I think it'll do the same thing in 3D. I actually had written a simulation because I had the same question. What does a 3D cell actually look like in CompuCell? And it's kind of tricky to address that issue, but what you can do is make a 3D grid of cells, make 2 cell types in the grid. The 2 cell types are exactly identical. Target volume, target surface, everything about the 2 cells is identical. You make the field 90% one cell type and 10% the other cell type. And then in CompuCell, you could tell it not to display one cell type. So you can hide the more common cell type. And your 3D display in CompuCell will just be 1 or 2 cells, random cells. And you can roll the simulation or roll the view around and see what that cell looks like in 3D. And I'll bet you that it will come very close to recreating what's this.
I mean, the one thing you have to think about if you're going to try to do complicated sputoid geometries like that is your lattice size has to be quite small. You need a lot of voxels per cell. And so then it becomes a fairly expensive computation to do. But it's nothing, no reason you can't do it. I also would say that probably if you're going to try to do that specific simulation, you want to use a hexagonal lattice rather than a square lattice. We haven't talked about lattice anisotropy very much, but the fact that we're on a lattice causes artifacts like lattice drag. If you got a square lattice lining up with the x and the y axis is lower energy than being perpendicular, being at a 45-degree angle or at another angle. And so you'll tend to see preferential alignment of edges along lattice symmetries. That problem is a little bit less severe when you go to a hexagonal lattice. It's easy to change in CompuCell, there's a simple tag that says hexagonal that'll take you from square to hexagonal lattice. And you don't really have to worry about things very much. Some of the measurements of distances are slightly different at hex lattices. But we don't tend to do it routinely in this introductory course material, but you can see online how to do it. And I would suggest doing that. Why don't you just try this out? In other words, make a layer of cells in 3D, start with them as cuboidal columns, and run it for some period of time, and then step through it and reconstruct the shapes. In other words, it would take maybe 20 minutes to write a simulation that would implement that. And I'd be fascinated. Why don't you, maybe after the break, you could come back and show us the results, show us some pictures of that. That would be fascinating.
Let's see. Any other questions?
Maish asked, "What's the most complicated imported image that's worked?" I'm not sure for whom, and what breaks down. One thing that certainly breaks down is the spatial resolution. If you make your lattice constant 2 microns, and your cells are 5 microns across, then you don't get a lot of spatial structure. CompuCell is not particularly good at very complex spatial structures. Cells like certain kinds of neurons or podocytes that have very complicated interdigitation, where there's a length scale in the cell that's very small compared to the typical size of the soma of the cell. Those are computationally expensive in any modeling framework. In a lattice method like CompuCell, the lattice size is the smallest thing you can represent. And so if you need to represent very tiny features, then you have to use a small lattice class. It's possible, but it's expensive computation. I think
histology images might be 10,000 by 10,000 pixels. So just a CompuCell simulation that big is doable, but it's going to be pretty slow. I've been reading in histology images and doing a scaling it down 10 to 1 on each axis. So my 10,000 by 10,000 histology images becomes 1,000 by 1,000 in CompuCell.
So I guess it matters a bit when you say complicated image, what kind of complexity you're talking about. Is that complexity the shape of the cell? Is the complexity the internal architecture of the cell? Is it three-dimensional relationships? We don't usually represent filopodia as CompuCell cells. We usually represent them as links, for example. So if you have not very thin fibers, we tend to represent them as links. Junctions are a little problematic in CompuCell. Although, as we've mentioned before a couple of times, Roland Burks has developed methods to try to represent junctions, and we heard a little bit about that in one of the hackathon presentations the other day. So, Maisha, I guess the thing to do would be if you, in the hackathon, we could sit down, look at some images with you, and ask the question, what's the most appropriate way to represent them?